Scientists discovered decades ago that stars at the edges of spiral galaxies orbit far too fast for the visible matter holding them in. In the year 14,000, the Future Archives cataloged the Kepler wafer, a silicon carbide star chart wafer, etched with rotation curves, baryonic mass profiles, and one repeated acceleration scale near 1.2x 10 or 10 meters per second squared. Which is the stranger possibility that galaxies are packed with invisible mass, or that gravity itself changes behavior when it grows weak. The wafer is small enough to rest in a human palm, and dense enough to preserve an argument that survived 10,000 years. Its etched tracks are not art. They are measurements. Radius in kiloparsecs, velocity in kilometers per second, gas mass, starlight, and along one surviving checksum ring, a repeated acceleration scale that appears again and again in galaxy dynamics. That detail matters because galaxies were never expected to be so orderly. If most of a spiral galaxy's mass sat where most of its light sits, orbital speeds should rise in the bright inner regions and then fall away outside them, the way planets farther from the sun move more slowly. That is the simplest Newtonian expectation when most of the gravitating mass is centrally concentrated. But when 20th century astronomers measured real galaxies, the outer parts often refused to slow down. The first strong shock came from optical spectroscopy. By splitting starlight and gas emission lines, astronomers could measure Doppler shifts on opposite sides of a galaxy disk. One side moved toward Earth, the other away. From that pattern, they reconstructed rotation speed as a function of radius, a rotation curve. And those curves kept flattening, not in one odd galaxy, in many. That is why this future wafer preserved curves instead of pictures. The mystery is encoded in the shape of the data. A flat outer rotation curve means that as radius increases, the enclosed gravitating mass must keep increasing too. Something beyond the bright stellar disk is still pulling. So, the opening question is not merely whether dark matter exists. It is why galaxies so often behave as though the missing gravity is organized, disciplined, and somehow tied to the ordinary matter we can actually see. To understand what the wafer records, we have to separate two ideas that are often blended together. The first is the missing mass problem. Measured gravity in galaxies appears stronger than the visible matter alone should produce. The second is the pattern problem. That extra gravity does not look random. Across many systems, the mismatch seems connected to the distribution of stars and gas. Those are not the same claim. A galaxy is built from baryonic matter. Stars, gas, dust, planets, people, everything made from familiar particles. When astronomers map a spiral galaxy, they can estimate where much of that baryonic mass sits by combining starlight, gas measurements, and models for stellar mass-to-light ratios. Then they can predict how fast matter ought to orbit if only that visible and inferable baryonic matter were gravitating. Often the prediction works reasonably well near the center, where stars are crowded. Then the outer galaxy stays too fast. By the late 1970s, radio observations of neutral hydrogen pushed those measurements much farther out than optical light alone could reach. Hydrogen emits at 21 centimeters, a wavelength that lets astronomers trace rotating gas well beyond the bright stellar disk. Those extended HI curves strengthen the case that spiral galaxies sit inside large, unseen halos. That conclusion remains part of standard astrophysics today. But the wafer points to a harder question. If dark matter halos explain the extra pull, why do the detailed acceleration patterns of galaxies so often track baryons with such consistency? Why should visible matter be such a good guide to total gravitational behavior? This is where the subject becomes more interesting than the phrase dark matter usually suggests. The puzzle is not simply hidden stuff in the dark. It is whether galaxies are revealing a deep law of structure formation or a deep law of gravity itself. There is a common mistake in popular explanations of this subject. They imply astronomers looked at a galaxy, found one number that was too high, and invented dark matter to fix it. The real evidence is richer than that. A rotation curve is a profile, not a point. It tells us how orbital speed changes from one radius to another. Different mass distributions create different curve shapes. A concentrated bulge, an extended disk, a diffuse halo. Each leaves a different dynamical signature. That means astronomers are not only inferring that extra mass exists, they are also inferring where that mass must be distributed. If velocity stays roughly constant with radius, then enclosed mass must continue rising roughly in proportion to radius. In plain terms, gravity is being supplied by something much more extended than the visible starlight. This is one reason dark halos became the standard picture. They do not just add extra mass, they add it in the right places. There is another detail the wafer silently preserves. The mismatch between baryons and total gravity is not strongest where gravity is strongest. In many galaxies, the discrepancy becomes dramatic in low acceleration outer regions. That observation later inspired a different line of thought. In 1983, Mordechai Milgram proposed MOND, modified Newtonian dynamics. The idea was not that astronomers had missed some ordinary matter, but that below a characteristic acceleration scale, dynamics might depart from the familiar Newtonian form. The exact proposal remains disputed, but the key insight was sharp. The anomaly might be linked to acceleration itself. That is why a tiny number etched into the wafer matters so much. About 1.2 x 10 dwarf 10 meters per second squared is not a random bookkeeping mark. It is close to the acceleration scale associated with MOND-like phenomenology, and later, with the radial acceleration relation. So, by the late 20th century, two broad interpretations were already on the table. Either galaxies contain large amounts of unseen matter, or galaxies are exposing a low acceleration regime where the usual gravitational rules are incomplete. If the story ended with spiral galaxies, modified gravity would be far more difficult to dismiss. It does not end there. The strongest reason most cosmologists still favor dark matter is that evidence for unseen gravitating mass appears on many scales at once. Galaxy clusters, gravitational lensing, the growth of large-scale cosmic structure, and the pattern of fluctuations in the cosmic microwave background all point in the same general direction. Most matter in the universe is not ordinary baryonic matter. That broader success matters. A good theory should not explain one class of observations by creating tension everywhere else. One of the most famous pieces of evidence arrived in 2006 with the Bullet Cluster, a collision between galaxy clusters. In X-rays, astronomers saw most of the hot baryonic gas, the dominant ordinary matter component in clusters, piled up and slowed by the collision. But weak gravitational lensing mapped most of the gravitating mass somewhere else, offset from that gas and closer to the galaxies, which largely pass through each other. That separation is hard to reconcile with the idea that all missing gravity is just hidden ordinary matter. It is also hard for simple modified gravity stories, because lensing and baryonic gas do not line up in the most straightforward way. This does not single-handedly solve the galaxy problem, but it changes the burden of proof. Any alternative to dark matter must now explain not only elegant galaxy rotation curve fits, but also merging clusters, lensing maps, cosmological structure growth, and the microwave afterglow of the early universe. That is why the consensus model, ΛCDM, remains the standard framework. Cold dark matter plus cosmic expansion history explains an enormous amount of data extraordinarily well. And yet, the wafer exists because galaxies still refuse to be merely messy examples of a solved theory. They seem to encode a regularity that standard dark matter language does not automatically make obvious. In 2016, a new phrase sharpened an old discomfort: the radial acceleration relation. Using high-quality galaxy datasets such as SPARC, astronomers compared two quantities across many points in many rotating galaxies. One was the observed acceleration inferred from the rotation curve. The other was the acceleration predicted from the measured baryonic matter alone. If galaxies were governed by wildly variable halo histories with no simple coupling to baryons, you might expect a broad scattershot cloud. Instead, the points fell along a remarkably tight relation. In the high acceleration regime, baryons already account for most of the gravity, so the relation approaches the Newtonian expectation. In the low acceleration regime, the discrepancy grows in a systematic way. That transition happens around the same acceleration scale that made MOND famous decades earlier. This is the reason the wafer preserved both rotation curves and baryonic profiles together. The issue is no longer just missing mass, it is correlation. Visible matter appears to predict total acceleration better than many people expected. Supporters of modified gravity saw this as a vindication. They argued that galaxies were indeed whispering the same rule. Supporters of dark matter saw something different. They argued that a tight relation can emerge if galaxy formation couples baryons and halos through repeated physical processes: gas cooling, star formation, supernova feedback, outflows, and the gravitational response of the surrounding halo. That is an important scientific distinction. The relation itself is established as an empirical finding, its interpretation is not, and interpretation is where this documentary begins to earn its future frame, because a civilization thousands of years later would not preserve this wafer to remember that galaxies were strange. It would preserve it because this was the benchmark data set against which competing ideas about gravity, dark matter, and cosmic structure were tested. That is the point where argument has to leave slogans and meet machinery. If the dark matter view is right, then the radial acceleration relation does not need a new law of nature. It needs a history, a real one. Gas falls into a halo. Some of it cools, some of it forms stars. Those stars flood their surroundings with radiation, stellar winds, and later supernova shocks. Gas is pushed outward, then rains back in, then is pushed again. Over billions of years, a galaxy is not a quiet disk settling into place. It is a repeatedly stirred gravitational system. That matters because dark matter, even if it barely collides with itself or with ordinary atoms, still responds to gravity. Change the mass distribution of the gas quickly enough, and the dark halo can be heated dynamically. Its dense inner cusp can soften into a core. In other words, ordinary baryonic violence can reshape invisible matter without touching it directly. This is not hand-waving. Hydrodynamic simulations in the 2010s and 2020s began showing exactly that in dwarf galaxies. Burst-driven outflows can flatten central dark matter density profiles if star formation is violent and repeated enough. That gave standard cosmology a serious answer to one of its sharpest small-scale problems. A halo predicted to be too dense in its center might not stay that way once real astrophysics is included. But solving the cusp core problem is not the same thing as explaining the full acceleration relation. A core changes the inner mass profile. The radial acceleration relation claims something broader. Across many radii and many galaxies, the total measured acceleration can often be inferred from the baryons with surprisingly little scatter. So the question becomes more demanding. Can feedback produce not just messy corrections, but a near-universal mapping between visible matter and total gravity? Some simulation teams say yes, at least in broad form. If galaxy growth follows a limited set of self-regulating pathways, then halos and baryons may converge towards similar outcomes. Star formation turns on only when gas reaches certain conditions. Feedback removes gas more easily from shallow potential wells than deep ones. Halo contraction or expansion depends on that same cycle. The result could be an emergent law, not fundamental, but repeated often enough to look fundamental. That idea is scientifically respectable, and still under pressure, because emergent regularities usually come with some environmental dependence, some assembly history memory, some extra scatter. If one dwarf formed stars in bursts and another formed them more gently, why should both land so cleanly on the same acceleration trend? Why should low-surface brightness galaxies, with very different visible structures, so often seem to know the same acceleration scale? That is why the wafer preserved overlays for halo fit and baryonic fit separately. Its makers were not asking whether simulations can make galaxies complicated. Of course they can. They were asking whether ordinary galaxy formation can make complexity converge into precision. And once a scientific argument reaches that level, the next step is no longer philosophy. It is measurement. The deeper challenge is scale. ΛCDM is not a galaxy theory alone. It is a universe theory. It earns its authority from many independent successes at once: the microwave background, large-scale structure, gravitational lensing, cluster growth, the abundance of light elements. That is why galaxy anomalies do not immediately overthrow it. A model that explains the cosmic web cannot be discarded lightly because disk galaxies are annoyingly elegant. But that same success raises the standard for any galaxy-scale explanation inside the model. If baryonic feedback is doing the work, it must do the work consistently across systems that should not share identical histories. Massive spirals, faint dwarfs, diffuse disks, gas-rich low-surface brightness galaxies, these are not clones. Their star formation histories differ. Their merger histories differ. Their environments differ. Their gas fractions differ. And yet, the observed relation between baryonic acceleration and total acceleration often looks smoother than that diversity would suggest. This is where active research becomes very technical, very fast. Scatter can be hidden or exaggerated by distance errors, inclination errors, beam smearing and radio observations, uncertain stellar mass-to-light ratios, or non-circular gas motions. A galaxy that appears to violate the relation may simply have its geometry wrong. A galaxy that appears to confirm it perfectly may be benefiting from careful sample selection. SPARC is high quality for a reason. It is not a random grab from the sky. That is an important scientific caution. A tight relation in a benchmark sample is not automatically a universal law in nature. At the same time, selection effects cannot explain everything away. The relation did not become famous because astronomers forgot how to handle uncertainties. It became famous because, after uncertainties were considered, the residual order still looked unusually strong. Then there are the dwarfs. Dwarf galaxies are precious in this debate because they are dark matter dominated over much of their extent. That makes them, in principle, cleaner laboratories for testing how baryons and halos couple. But dwarfs are also observationally fragile. Their gas can be turbulent. Their disks can be irregular. Their rotational support can be incomplete. Some are so faint that every inferred parameter carries large error bars. So, dwarfs do two contradictory things at once. They may hold the clearest clues, and they may be the easiest systems to misread. This is exactly the kind of scientific tension future archivists would preserve. Not a solved mystery, but a narrowing battlefield. By the era that stored this wafer, the debate was no longer over whether the mismatch existed. It was over whether better data would wash the Elegance out, or make it impossible to ignore. This is why modified gravity never disappeared. Not because it won the cosmological case. It did not. And not because most physicists think the problem is solved by replacing dark matter. They do not. Modified gravity ideas remain alive because at the level of individual galaxies, they often do something dark matter models struggle to do elegantly. They predict a rule first. MOND, in its original form, introduced a characteristic acceleration scale below which dynamics depart from the familiar Newtonian expectation. Above that threshold, ordinary gravity works as usual. Below it, the effective gravitational response changes in a way that can raise orbital speeds without adding an unseen halo to each galaxy. That is why the number on the wafer matters. It is not just a fit parameter. It is the hint that many different galaxies may be crossing the same physical boundary. One genuine lesson here is easy to miss. MOND is not mainly about faster stars at the edge of galaxies. It is about dimensional structure. An acceleration scale has units. It marks a regime change. In physics, regime changes are often where deeper theories announce themselves. That is the seduction. With relatively few inputs, MOND-like formulas can fit many rotation curves remarkably well. In some cases, once the visible mass distribution is known, the shape of the rotation curve follows with far less halo freedom than standard fitting might suggest. For supporters, that is not an aesthetic bonus. It is evidence that galaxies are obeying a low acceleration law. But here the documentary has to become stricter, not looser. A successful galaxy fit is not enough. Any alternative to dark matter must also face galaxy clusters, relativistic lensing, the growth of structure across cosmic time, and the microwave background. That is where modified gravity programs have struggled. Extensions exist. Tensor vector scalar frameworks and other relativistic variants were built precisely to widen MOND beyond disk galaxies. Yet none has replaced ΛCDM as the broad consensus description of the universe. The bullet cluster remains especially stubborn. In that collision, the hot X-ray gas, most of the ordinary baryonic mass, is offset from the lensing mass peaks. Something gravitating behaved as if it passed through the collision more cleanly than the gas did. That is hard to wave away if one wants a Baryons-Only universe. So, the modified gravity case is strongest where the wafer points, and weakest where the wider universe pushes back. That asymmetry matters. It means the scientific choice is not between a theory that works and one that fails. It is between one framework that is globally successful but locally awkward, and another that is locally elegant but globally burdened. And that is a far more interesting problem than a simple missing matter story. By this point, the wafer no longer looks like a record of galaxies. It looks like a fork in method. One path says the relation is emergent. Dark matter is real, general relativity survives, and galaxy formation is a self-regulating machine more precise than anyone first expected. In that future, the mystery is not new gravity. It is why feedback, gas cooling, halo response, and star formation thresholds together generate such reliable order. A second path says the order is too sharp to be accidental. The acceleration scale is telling us something fundamental. Galaxies are exposing a low acceleration regime where the effective law changes. In that future, dark matter may be reduced, reinterpreted, or made unnecessary on galaxy scales, even if some broader cosmological supplement still has to be invented. A third path keeps the unseen matter, but changes its character. Maybe dark matter is not simple, cold, and almost perfectly collisionless. Maybe it has self-interactions. Maybe the dark sector contains additional forces or pressure-like behavior. Maybe those properties reshape inner halos and tighten the coupling to baryons in ways minimal dark matter never could. That possibility is attractive because it preserves the broad cosmological triumphs of unseen matter while admitting that the particle picture might still be incomplete. Each path has a cost. The first must explain precision without hidden fine-tuning. The second must survive clusters, lensing, and cosmology. The third must make predictions sharp enough to be falsified, rather than endlessly adding flexibility after each new observation. This is why the debate has lasted. The strongest options are not absurd. They are all scientifically serious enough to survive contact with data, and all vulnerable enough to remain unfinished. From the perspective of year 14,000, that is exactly when an archive object becomes worth preserving. Not when the answer is obvious, but when a scientific culture realizes it has found a regularity that could split theory three ways. The abrasion on the wafer's outer edge makes more sense here. This was likely not ceremonial. It was handled, indexed, compared, probably against later datasets built with better distance ladders, wider hydrogen surveys, sharper lensing maps, and simulations no 21st century machine could run. In other words, this object may mark the moment when astronomy stopped asking only, "Where is the missing mass?" and started asking, "Why does the missing mass seem to know where the visible matter lives?" If you're enjoying this investigation, subscribe to future archives. There is another recovered mystery waiting. So, what would decide it? Not one dramatic image, not one perfect galaxy, and almost certainly not one argument repeated more loudly. The winning evidence would have to connect scales. For the dark matter emergent view, the task is clear. Simulations and surveys must show that the observed acceleration relation appears naturally across the full diversity of galaxies, including difficult dwarfs, ultra-diffuse systems, and unusual environments, without choosing parameters case by case until the answer appears. The model has to earn the relation as an outcome, not assume it as a target. For modified gravity, the burden is equally sharp. A viable theory must keep its galaxy-scale elegance while matching relativistic lensing, cluster collisions, cosmic microwave background constraints, and structure growth. It is not enough to say galaxies look cleaner this way. The universe is the full exam. For non-standard dark matter, the requirement is prediction. Self-interactions or richer dark sector physics must produce distinctive signatures in halo shapes, core sizes, mergers, or substructure that can be tested independently. Otherwise, the idea risks becoming a storage room for unresolved tensions rather than an explanation. There is also a quieter frontier, measurement discipline. Astronomy often turns philosophical too early. Before declaring a new law or a new particle property, researchers have to beat down the ordinary errors. Distance calibration, stellar population modeling, gas geometry, beam smearing, asymmetric drift, unresolved non-circular motion. A few percent here, a few percent there, and a supposedly profound law can tighten or loosen dramatically. That may sound mundane. It is not. Science advances because instruments become less forgiving of our stories. Which brings the investigation back to the wafer itself. A long-term calibration archive only makes sense in a culture that expected the debate to continue across generations of better measurements. The etched fiducials in kiloparsecs and kilometers per second, the preserved acceleration checksum, the separate overlays for baryonic-only, halo, and modified dynamics fits. All of it suggests a benchmark meant to be revisited as methods improved, so the artifact does not tell us which side won, not yet. What it tells us is more disciplined than that. At some later point in human inquiry, this pattern was still important enough to test against new evidence, not merely admire. That means the real scientific question survived its first wave of explanations. And that leaves us with the debate the wafer still carries forward. When galaxies track their visible matter this closely, are we seeing invisible mass disciplined by galaxy formation? Or the first clean sign that gravity itself changes in the weakest fields? The first possibility to eliminate is also the simplest, that astronomers merely underestimated ordinary matter. That sounds reasonable until the accounting is actually done. In a spiral galaxy, the visible budget is not just stars. It includes cold gas, especially hydrogen traced at radio wavelengths, molecular clouds inferred more indirectly, dust, stellar remnants, and the uncertainty in how much mass a given amount of starlight really represents. Modern rotation curve work does not ignore those ingredients. It builds them in. That is what the wafer's stacked profiles imply. Separate tracks for starlight, separate tracks for gas. Then the baryonic prediction assembled from both. Only after that does the mismatch appear. And the mismatch is structured. If visible matter alone governed the outskirts, orbital speed should usually fall with radius, because most of the bright mass is concentrated toward the center. Under Newtonian gravity, less enclosed mass growth means less centripetal support at large distance. Yet many galaxies do something else. Their outer curves stay high, sometimes almost flat. Sometimes they rise more gently than the luminous profile would ever permit. One of the most important facts here is easy to miss. Hydrogen often extends farther out than the stellar disk. Radio astronomers use that fact to test gravity where accelerations are weakest. So, the outer rotation curve is not a decorative edge case. It is where the argument sharpens. Could hidden baryons still rescue the story? Not in the amounts required, at least not by known forms of ordinary matter. If a galaxy held enough unseen normal material to replace a dark halo, that material would tend to leave other fingerprints. Emission, absorption, chemical consequences, dynamical heating, or conflict with larger cosmological baryon limits inferred from the early universe. The room for concealment is real, but not infinite. So, one path closes. The galaxies are not simply asking for a bit more gas and a bookkeeping correction. They are asking for either a new gravitating component beyond familiar matter, or a new rule for motion in weak gravitational fields. And that is why the wafer preserved 3 overlays instead of 1. Then came the more unsettling result. Rotation curves had already shown that galaxies need something extra under standard gravity. The radial acceleration relation changed the tone of that claim. Instead of asking only how much mass is missing, it asked how the discrepancy scales with the gravity expected from visible matter itself. The procedure is straightforward in principle. At each radius in each galaxy, one computes the acceleration predicted by the observed baryons, stars plus gas. Then one compares it with the acceleration actually required by the measured orbital speed. If galaxies were wildly idiosyncratic systems, those points might scatter broadly. Formation histories differ. Merger histories differ. Star formation is messy. Gas is turbulent. Yet the SPARC analysis reported something much tighter than that intuition suggests. Across many spirals with different sizes and surface brightnesses, the observed acceleration followed a narrow trend with a baryonic prediction. In the high acceleration inner regions, baryons nearly suffice. In the low acceleration outskirts, the discrepancy grows in a regular way. This is the scientific reason the checksum ring on the wafer matters. The value near 1.2 times 10 to the minus 10 meters per second squared is not just a fit parameter in an obscure model. It is close to the acceleration scale at which the behavior changes. Above it, Newtonian expectations from baryons work better. Below it, galaxies begin to act as if an additional rule enters. That does not prove modified gravity. It proves a regularity. And regularities are dangerous. They can be clues to deep law or clues to hidden selection effects, coupled astrophysical processes, and data pipelines that have become more disciplined than our first intuitions. This is why serious astronomers argued over scatter. If the relation is truly as tight as first reported, some versions of dark matter galaxy formation have an explanation burden. If the relation broadens once distance errors, inclination errors, beam smearing, non-circular motions, and stellar mass-to-light uncertainties are pushed fully through the calculation, then some of the apparent elegance may soften. So, the acceleration plot did not end the debate, it refined it. The puzzle was no longer just missing mass. It was missing mass that seemed to know exactly where the baryons were. If the broad cosmological case for dark matter remains strong, and it does, then the next question becomes more precise. Not, does dark matter exist anywhere? But, why should dark matter and baryons correlate so cleanly inside individual galaxies? There is a standard answer in outline. Galaxies form inside dark matter halos. Gas falls into those halos, cools, settles, forms stars, explodes as supernovae, launches winds, and responds to the halo's gravitational potential while also reshaping it. That feedback loop can be violent. Repeated bursts of star formation can shove gas outward, change the central potential, and in simulations, even turn a steep inner dark matter cusp into a flatter core. That last point matters because it was once treated as a serious small-scale challenge. Pure collisionless cold dark matter simulations often produce dense central cusps. Some observed dwarf galaxies appeared to prefer gentler cores. Hydrodynamic simulations showed that ordinary astrophysics is not a minor correction here. Baryons can move enough mass around to alter the inferred dark distribution itself. So, dark matter is not a rigid invisible scaffold with stars sprinkled on top. The two components co-evolve. That makes an emergent acceleration relation conceivable. If halo growth, gas cooling, angular momentum, star formation thresholds, and feedback all couple in repeatable ways across galaxy types, then visible matter could become a good predictor of total acceleration without any need to modify gravity. But conceivable is not the same as demonstrated. The hard part is reproducing both the existence and the tightness of the relation across dwarfs, low surface brightness galaxies, and large spirals without quietly tuning many freedoms after the fact. A successful explanation has to survive the messy diversity of real galaxies. And there is another constraint. Whatever mechanism works cannot break the things standard cosmology already gets right. Large-scale structure, microwave background fits, lensing statistics, and the growth history of the universe. So, the dark matter position is stronger than its critics often admit, and more burdened than its defenders sometimes say. It does not merely need extra mass. It needs a reason that extra mass so often arranges itself in dialogue with ordinary matter. This is where the modified gravity camp has always pressed its advantage. If a single acceleration scale organizes galaxy dynamics, why bury that regularity inside complicated formation histories? Why not take the data at face value and say that below a threshold acceleration, motion departs from the Newtonian form? That was the original attraction of MOND in the early 1980s. With very few ingredients, it could fit many rotation curves remarkably well. For a working astronomer, that elegance is not cosmetic. It means fewer arbitrary halo choices from galaxy to galaxy. It means the luminous distribution itself carries more of the predictive power. There is also a genuine scientific virtue in how risky that claim is. A theory that says weak accelerations obey a modified rule can be sharply tested. And in many disk galaxies, that rule captures the observed pattern surprisingly well. But elegance on one scale is not enough. The universe has to agree everywhere. Galaxy clusters remain a major stress point. Even with modified dynamics, many clusters still appear to require additional unseen mass. Then there are emerging systems like the bullet cluster, where weak lensing maps place most of the gravitating mass away from the dominant hot gas seen in X-rays. That observation is not a casual inconvenience. It is one of the clearest pieces of evidence that much of the gravitating matter behaves as a collisionless component rather than ordinary baryonic plasma. A modified gravity advocate can respond in several ways. Perhaps the relativistic completion of the theory is incomplete. Perhaps some unseen matter still exists, but less of it, or in a different role. Perhaps cluster environments probe a regime where the simple galaxy-scale rule is not the whole story. Those are serious responses, but they come with a cost. The more extensions needed to save galaxy elegance on larger scales, the less decisive that elegance becomes. So, modified gravity gains power from the wafer's acceleration checksum, and from the tightness of disk galaxy data. It loses power wherever mass maps, cosmology, and structure growth demand a framework broader than a beautiful galaxy law. There is a third path between standard cold dark matter and modified gravity. And it matters because it preserves the core evidence for unseen mass while admitting that the simplest particle picture may be incomplete. In that view, galaxies are not telling us gravity is wrong, they are telling us the dark sector has structure of its own. The default cosmological model often treats dark matter as cold and effectively collisionless. That approximation works extremely well for the large-scale universe. But if dark matter particles can scatter weakly off one another, or carry additional dark sector interactions, then halo centers can be reshaped. Densities can soften, responses to baryonic activity can change. Coupling between visible and dark distributions may become tighter than in the simplest halo picture. This is not license for endless model building. The danger is obvious. A theory with too many knobs can explain every anomaly after it appears and predict nothing beforehand. That is why the best dark sector proposals are judged by whether they make distinct, falsifiable signatures. Altered halo shapes, characteristic core sizes, changes in substructure, lensing effects, or consistency with particle physics constraints. The important scientific fact is that galaxy dynamics do not merely test astronomy, they test microphysics by proxy. A rotation curve is an orbit measurement, yes, but it may also be a clue to how any unseen particles interact, cluster, and exchange energy over cosmic time. From the perspective of the wafer, this third option is almost inevitable. A benchmark archive built for repeated comparison makes the most sense in a scientific culture that expected model revision, not a clean two-sided duel. Baryons-Only had already failed. Standard halos faced pattern constraints. Modified gravity faced cluster and cosmology constraints. So, the live frontier would naturally shift toward hybrid explanations and sharper diagnostics. That is the deeper message in the abrasion on the wafer's rim. It was handled in an era when the argument had become less ideological and more forensic. Not dark matter or gravity in the abstract, but which version of matter, which version of gravity, and which measurement would finally separate them. That forensic turn leads to a simple conclusion. If the major frameworks are still both alive, then the next evidence must come from systems where their predictions separate cleanly. Not the grand spirals already polished into benchmark plots, the awkward cases, dwarf galaxies, ultra-diffuse galaxies, satellites scraped by tides, systems with so little starlight that every assumption about mass-to-light ratio matters less, and every assumption about dynamics matters more. This is one reason low-mass galaxies became so important. In a massive bright spiral, one can hide uncertainty inside stellar populations, gas corrections, bulge structure, and distance errors. In a faint dwarf, the visible matter budget is smaller and often gas-rich. The mismatch between baryons and motion can become more extreme. That makes dwarfs harsh laboratories for both dark matter and modified gravity. Establish science first. Under standard cold dark matter expectations, the smallest halos should be especially dark matter dominated. Their stars are only a thin, luminous tracer buried inside a much larger halo. But that clean picture was challenged by a long list of small-scale tensions. Cusp versus core, too big to fail, satellite diversity, and the fact that galaxies with similar total mass can show very different inner rotation speeds. That last point matters more than it sounds. If two galaxies live in similar halos, why does one rise steeply in its inner rotation, curve, while another stays shallow? A single universal halo recipe struggles there. Baryonic feedback offers one answer: repeated bursts of star formation can drive gas out and back in again, changing the central gravitational potential. Over time, that gravitational stirring can lower the central dark matter density, replacing a steep cusp with a softer core. This is not hand-waving. Hydrodynamic simulations in the 2010s and 2020s showed that baryons can reshape dark matter, especially in dwarfs. But the effect is conditional. Too little star formation, and there is not enough energy to stir the halo. Too much mass, and the inner potential may remain difficult to transform. So, core formation is not a free pass. It predicts a pattern. The impact of feedback should depend on galaxy mass and star formation history. Modified gravity advocates read the same systems differently. For them, dwarfs are not messy exceptions. They are deep into the low acceleration regime, where the modified rules should be most visible. If the acceleration scale is fundamental, these galaxies ought to line up naturally once the baryons are measured well enough. So, the weak point becomes the measurement itself. Dwarfs are faint, their gas can move non-circularly, their inclinations can be uncertain, radio beams can blur inner structure. A tiny distance error changes the inferred mass and radius together. Some of the sharpest arguments in this field are not about equations at all, but about whether the observed inner slope of a dwarf galaxy is real, or partly an artifact of how the data were extracted. That is why the wafer matters as a calibration object. It does not preserve only elegant curves. It preserves comparison logic, halo fit, modified dynamics fit, baryonic fit. In other words, a scientific culture preparing for a verdict from difficult galaxies, not easy ones. And the uncomfortable possibility remains that the decisive evidence may not come from the average case at all, but from the outliers each framework would rather explain away. By this stage of the argument, the most valuable galaxy is not the one that fits beautifully, it is the one that should not. Astronomy has already produced several such cases. Galaxies reported with surprisingly low, inferred dark matter content. Others claim to be too diffuse for standard expectations. Others again whose satellites seem to line up in planes, or whose internal motions look too ordered, too shallow, or too odd for a simple halo picture. Some of these claims later weakened under better data. Some survived in altered form. That instability is itself a lesson. The lesson is that galaxy dynamics are not measured directly. Telescopes record light, spectral shifts, and in radio surveys the velocity of gas spread across a beam with finite resolution. Mass is inferred, geometry is inferred, inclination is inferred. Even the distinction between ordered rotation and pressure support can matter. In small galaxies, a difference of a few kilometers per second is not noise in the casual sense. It can decide whether a system seems to demand a cusp, allow a core, or fit a low acceleration law. This is why strong claims in this field often travel with unusually technical disputes. One group adjusts the distance ladder, another remeasures the inclination from a warped gas disk, another models asymmetric drift, where random gas motions help support the system, so the true circular speed differs from the observed mean. A galaxy can move from scandal to ordinary once these corrections are applied, but not all tensions disappear that way. Some outliers remain instructive because they test how much freedom each theory really has. Standard dark matter can absorb irregularity if galaxy formation is stochastic enough. That is a strength because real galaxies are messy. It is also a weakness because too much flexibility makes prediction soft after the fact. Modified gravity gains force from needing fewer ingredients at galaxy scale, yet outliers are painful there too, because a universal acceleration law has less room to maneuver when a galaxy refuses to follow the expected baryon motion link. This is where selection effects enter the investigation. The cleanest benchmark samples are not random slices of the universe. They are galaxies with sufficiently good inclinations, resolved kinematics, and usable photometry to support precision fitting. That is scientifically sensible. It also raises a hard question. Is the remarkable tightness of the radial acceleration relation partly a truth about nature, or partly a truth about which galaxies become precision data sets? That is an active research question, not a settled criticism. The relation is real as an empirical fit. The dispute is over how universal and how scatter-free it remains once lower quality systems, unusual environments, and full systematic uncertainties are propagated consistently. Notice what this does to the debate. It shifts the burden from rhetoric to survey design, better distance indicators, better radio resolution, better modeling of non-circular motion, larger samples of low-surface brightness galaxies, cleaner weak lensing comparisons. The theory argument becomes an engineering argument. And that, again, explains the wafer's survival. A civilization does not machine a radiation-hard benchmark standard unless it expects the same curves to be remeasured, reprocessed, and argued over across generations. The hidden assumption in every elegant fit is that the data are already telling the truth clearly enough. The next century of astronomy was built to test whether that confidence was deserved. Once the argument reaches that level, another possibility becomes hard to ignore. Dark matter may be real, and the simplest version of dark matter may still be wrong. That distinction is essential. Much of the public debate collapsed too many ideas into one, as if rejecting one clean, collisionless, perfectly cold particle picture would automatically vindicate modified gravity. Science does not work that way. A failed implementation can strengthen the case for a broader category without preserving its first draft. Established evidence already points strongly toward unseen gravitating mass on large scales. The cosmic microwave background, structure growth, and lensing all support that. The open question is whether the dark sector has internal physics rich enough to matter inside galaxies. One leading line of active research asks whether dark matter particles might interact with one another, not strongly enough to become ordinary matter, but enough to exchange momentum in dense regions. Self-interacting dark matter can soften inner halos, potentially helping with core formation and some small-scale tensions. Another line considers warm dark matter, where particles move fast enough in the early universe to suppress some of the smallest structures. Other proposals invoke multiple dark components, dark radiation, or couplings that alter how halos assemble. These are not interchangeable patches. They make different predictions. Self-interactions can change halo shapes and the survival of substructure. Warm dark matter affects the abundance of small halos from the start. Mixed dark sector models can alter both cosmological growth and galaxy-scale structure. The challenge is the same as always. Improved fit is not enough. The model must predict something distinctive before the data are tuned around it. There is a deeper reason these ideas matter for the wafer's checksum ring. A characteristic acceleration scale can emerge in more than one way. In modified gravity, it may be fundamental. In a complex dark sector, it may be effective, a recurring outcome produced by halo assembly, baryonic thresholds, and dark sector response. Those are philosophically different explanations, even if some galaxy curves look similar. This is where many discussions become sloppy. A recurring number in nature does not automatically prove a new law. Planetary atmospheres, nuclear transitions, and fluid turbulence all show preferred scales that emerge from underlying processes without being fundamental constants of motion. The scientific task is to determine which kind of scale this is. If future observations showed that galaxies obey the acceleration relation with tiny scatter across extreme environments, tidal histories, and masses, the case for a fundamental rule would strengthen. If instead the relation broadens in exactly the way feedback and dark sector microphysics predict, then dark matter would not merely survive. It would become more interesting. From the far future, that is one of the most revealing things about this archive. The wafer records one number almost reverently, but it also preserves multiple overlays for how that number should be interpreted. Whoever built it understood that matching the same curve is not the same as telling the same physical story. So, what future would a careful scientist of the early archive age have considered most plausible? Not a sudden overthrow, not a clean surrender by one side. Convergence. That is informed speculation, grounded in the evidence already on the table. Large-scale cosmology was too successful for any galaxy-scale anomaly to erase lightly. At the same time, the baryon acceleration regularity was too persistent to dismiss as coincidence. The likely path was therefore a layered solution. Dark matter remains, but the connection between visible matter and total gravity becomes less mysterious as simulations, surveys, and theory mature together. The first step in that path is technical, not philosophical. Better observations push rotation curves farther out and resolve them better in the center. gas maps improve, distances tighten. Stellar mass estimates benefit from better infrared photometry and stellar population modeling. Weak lensing around galaxies and groups adds an independent check on mass distributions. The relation between baryons and total acceleration is then measured not as a slogan, but as a full probability distribution with known systematics. The second step is computational. Galaxy simulations stop treating baryons as a nuisance correction and begin treating them as co-authors of halo structure, bursty star formation, cosmic inflow, black hole feedback in larger galaxies, magnetic fields, turbulence, and environmental stripping all alter where baryons settle and how halos respond. In such a program, regularity does not have to be put in by hand. It can emerge if the same physical thresholds recur across cosmic history. The third step is discriminating prediction. Theories are forced to risk failure in advance. Does the scatter and the radial acceleration relation increase at the faintest masses? Do satellite galaxies in strong tidal fields deviate systematically? Do lensing-based mass estimates track the same law as internal gas kinematics? Does the relation evolve with redshift when galaxies were more gas-rich and more turbulent? These are not side issues. They are where emergent regularity and fundamental law explanations begin to pull apart. From our distance in time, this convergent path has a practical elegance. It does not ask one community to admit total defeat. It asks every community to surrender its easiest version. Minimal cold dark matter gives way to a richer account of galaxy assembly. Pure galaxy-scale modified gravity must survive cross-scale tests or retreat. Exotic dark sector models must stop being adjustable umbrellas and become predictive. This is often how mature science advances, not by rewarding the boldest slogan, but by compressing several vague stories into one narrower and harder-to-escape explanation. If that happened here, then the wafer was not a relic of confusion. It was a tool from the transition. A standard carried forward while astronomers moved from asking whether galaxies needed extra gravity to asking exactly how ordinary matter taught invisible mass to leave such a reproducible signature. There is, however, one reason the modified gravity case never vanishes completely. Its central success is too sharp. A great many galaxies appear to know about their baryons with a simplicity that standard lore did not predict in advance. For critics of the dark matter consensus, that remains the wound in the theory. It is not enough to say that simulations can be made more realistic. The question is whether they produce the right regularity for the right reason across the full diversity of galaxies without hidden tuning. That is the strongest competing viewpoint the wafer preserves. Not that dark matter has no evidence. It plainly does, especially beyond galaxy scale. The stronger critique is narrower and more serious. Perhaps the galaxy data are pointing to a low acceleration principle so basic that dark matter explanations only imitate it imperfectly. If that were true, the implications would be enormous. The anomaly would not be a bookkeeping problem about unseen mass. It would be a clue that gravity, inertia, or space-time has an effective regime not captured by the standard weak field picture at extremely low accelerations. That would place galaxy disks in the same historical category as Mercury's orbit before general relativity, or blackbody radiation before quantum theory. Not contradictions everywhere, but precision cracks in a successful framework. This remains speculative and disputed. Any such theory still has to face clusters, merger systems, cosmology, and relativistic consistency. Those demands are severe. Many proposed extensions become less elegant the moment they leave the galaxy scale. Still, severe is not the same as impossible, and science has a duty to distinguish between a theory that is disfavored and a theory that has actually failed. That is why the final meaning of the wafer is more subtle than a winner's trophy. Its tungsten traces do not commemorate a solved mystery. They preserve the exact place where one side had breadth and the other had elegance. And the universe had not yet revealed whether those would ever become the same thing. The opening artifact now reads differently, not as a shrine to one magical number, but as evidence that generations of astronomers kept finding the same disciplined irritation. Galaxies do not merely seem heavy, they seem organized. So the debate that survives this archive is precise. When visible matter predicts motion as well as it often does, should that be read as unseen matter shaped by regulated galaxy formation, or as the signature of a deeper low acceleration law that larger-scale cosmology has not yet fully absorbed? That is the question this wafer was built to keep alive. Let me know in the comments which assumption you think is doing more hidden work: the physics of the dark sector, or the idea that gravity itself stays unchanged all the way down to these tiny accelerations. Seen this way, the wafer becomes more revealing than a summary ever could be. It does not preserve a verdict, it preserves a protocol. The etched overlays for baryons alone, halo fit, and modified dynamics sit on the same physical object because the builders were not commemorating a solved problem. They were standardizing a comparison. That matters. In science, a benchmark is what survives when a field expects arguments to continue across generations. And that tells us something concrete about the state of the evidence in their era. If one explanation had crushed the others beyond serious dispute, there would be little reason to keep all three reconstruction layers indexed together with the same radius and velocity scales. The wafer instead behaves like a calibration key. Feed in a galaxy. Compare the residuals. Ask which framework fails first. That is exactly how mature astronomy often proceeds. Not by chasing one beautiful idea, but by forcing rival ideas to survive the same measurements. There is another clue in the object itself. The checksum ring does not merely store an acceleration scale. It stores it as a fitted reference attached to a population of galaxies, rather than to one especially dramatic case. That points to a discipline that had moved beyond anecdotes. Not one strange galaxy, not one inconvenient rotation curve, a whole ensemble. This is an important scientific shift. Early dark matter arguments were compelling because the mismatch between visible matter and orbital speed kept recurring. Later, work raised the standard. It asked whether that mismatch also followed a repeatable mathematical relation across many galaxies with different masses, gas fractions, and surface brightness. The radial acceleration relation was powerful because it turned a collection of problems into one sharper question. Why should systems with wildly different histories line up so well at all? That question remains hard inside ordinary galaxy formation, because galaxies are not tidy machines. They accrete gas unevenly, they merge, they blow matter out through stellar winds and supernova explosions. Bars redistribute angular momentum. Black holes can heat gas in larger systems. Even measuring a rotation curve is not trivial. Astronomers must infer inclination, convert light into stellar mass, track gas out to faint outer radii, and correct for non-circular motions. A relation that survives all of that clutter is immediately more interesting than a relation drawn from idealized textbook disks. That is why some researchers treated the acceleration scale almost the way atomic physicists treat a spectral line, not as proof by itself, but as a recurring signature demanding explanation. Still, the wafer's structure also reveals caution. Its data tracks show abrasion near several outer radius points, yet the overlay indices remain preserved. That suggests the specific numbers could degrade without destroying the object's purpose. The purpose was comparative. The builders needed later analysts to know which hypothesis was being tested against which observational profile. So, the artifact does not say gravity was modified. It does not say dark matter won. It says something subtler. By the era that archived this standard, astronomers believed the real danger was not missing the anomaly. It was explaining it too quickly. And that restraint points forward to a larger possibility. Perhaps the final answer was never expected to be a simple either-or at all. Perhaps the future this wafer anticipated was one in which dark matter remained real, gravity remained largely intact, and the deeper discovery lay in understanding why galaxy formation kept translating one into the language of the other. If that is right, then the object is not preserving a crisis. It is preserving the moment the crisis became a precision science. If a problem survives for decades, the next advance is often not a new slogan. It is better measurement. For this question, that means pushing into the galaxies that are hardest to model and easiest to ignore. Tiny dwarfs with irregular gas motions, ultra-diffuse galaxies with very little starlight, edge-on systems where inclination is treacherous, remote galaxies where distance errors distort mass estimates. The clean relation is most persuasive if it keeps surviving where the data become ugly. That may sound technical, but it changes the interpretation completely. Take distance alone. If a galaxy is closer or farther than assumed, its inferred luminosity changes, its stellar mass changes, and even the mapping between angular size and physical radius shifts. A rotation curve can look more or less consistent with a proposed law simply because the distance ladder moved underneath it. Inclination errors do something similar. If a disk is more face-on than astronomers think, its true rotation speed is higher than the line-of-sight measurement first suggests. Small geometric mistakes become dynamical arguments. This is one reason the debate lasted. The galaxy scale pattern is real as an observational claim, but the exact scatter around it carries much of the theoretical weight. A very tight relation can look almost law-like. A broader one can look like the outcome of formation history plus measurement uncertainty. Future radio surveys mattered because hydrogen gas extends far beyond the brightest stars. That lets astronomers trace gravity into outer regions, where dark matter effects become hardest to dismiss, and where low acceleration behavior becomes most exposed. Better infrared measurements mattered too, because near-infrared light traces older stellar populations more reliably than blue light, flooded by recent star formation. Better stellar masses mean better baryonic acceleration estimates. Weak lensing adds another route. On a single galaxy basis, lensing is difficult. But statistically, large samples can reveal how halo mass relates to visible structure without depending only on rotation curves. If lensing-derived halo profiles line up with the same baryonic predictors, the dark matter interpretation gains independent support. If they resist the expected mapping, the pressure on standard models grows. There is also the time dimension. Most of the classic debate was built from nearby galaxies in the relatively recent universe. But galaxies were rougher in the past. Star formation rates were higher, gas fractions were larger, mergers were more common. If a tight acceleration relation is already present in those earlier, messier systems, then an emergent explanation must work under harsher conditions. If the relation tightens only later as galaxies settle, that would favor the idea that long-term self-regulation is doing much of the work. This is where the speculative future implied by the wafer becomes disciplined rather than fanciful. A civilization preserving a benchmark like this may have inherited surveys spanning not thousands, but millions of resolved galaxies across cosmic time. That is speculation about scale, but not about method. The method is familiar. Enlarge the sample, reduce the systematics, test the extremes, and those extremes matter because each rival view has a weakness it cannot hide forever. Modified gravity ideas must survive clusters, cosmology, and relativistic consistency. Minimal cold dark matter must explain why visible matter predicts total acceleration with such economy. Non-standard dark sectors must stop being infinitely adjustable and make hard predictions that differ from baryonic feedback alone. So, the tie does not break when one camp writes a clever paper. It breaks when the awkward galaxies stop cooperating with one side. The wafer implies that, for a long time, they had not. So, what future does the evidence favor most strongly? Not a clean overthrow, not a perfect triumph. The most plausible path is convergence under pressure. Established science already leans heavily one way on the largest scales. The microwave background, large-scale structure, and gravitational lensing all support a universe with substantial non-baryonic gravitating matter. That backbone is difficult to discard without replacing an enormous amount of successful cosmology. Any future explanation that abandons dark matter entirely has to rebuild far more than galaxy rotation curves. That is why the most defensible forecast begins with dark matter staying. But staying is not the same as remaining simple. The likely evolution is that galaxy dynamics became a laboratory for how baryons sculpted the observable expression of dark halos, and possibly for whether the dark sector possessed richer microphysics than the earliest cold collisionless picture assumed. In that future, the acceleration scale preserved on the wafer would not be elevated to a new law of nature in the strictest sense. It would be recognized as an emergent regularity, a compressed summary of how gas cooling, star formation thresholds, feedback cycles, halo response, and environmental history cooperate across a wide range of galaxies. That is informed speculation. Why call it the most plausible path? Because it asks the fewest things to be wrong at once. It keeps the cosmological successes already measured. It keeps the empirical galaxy relation astronomers actually saw. And it turns the puzzle into a demand for deeper galaxy formation physics rather than a wholesale rewriting of gravity. There is precedent for this kind of scientific outcome. Temperature and pressure once looked like basic substances in their own right. Later, they became emergent descriptors of microscopic motion. In the same way, a characteristic acceleration could turn out not to be a fundamental constant of gravity, but a macroscopic fingerprint of how luminous matter settles inside halos under recurring physical limits. Yet this path has a price. It requires that simulations stop merely matching broad trends and start predicting narrow regularities before observers ask for them. The danger for standard cosmology has never been lack of flexibility. It is too much flexibility. If every new galaxy can be explained after the fact by adjusting feedback history, then explanation becomes bookkeeping. That is why the future archive matters. A benchmark wafer only makes sense in a scientific culture that demanded pre-registered confrontation between data and model. The object implies that later astronomers knew elegance can mislead, but so can a model with enough knobs to fit anything. There is also a second plausible branch, weaker but still alive. Dark matter may endure, yet not in its minimal form. Self-interactions, dark radiation in the early universe, or other dark sector effects could alter halo structure and naturally tighten the link between visible matter and total acceleration. That route preserves unseen matter while admitting that the invisible component had its own internal physics, not just passive mass. Notice what has happened by this stage of the investigation. The old public argument, dark matter or modified gravity, has narrowed. The more realistic scientific contest may be this. Is the galaxy pattern an emergent property of ordinary baryonic regulation inside largely standard halos? Or is it the first visible sign that the dark sector itself is more structured than the simplest model allowed? That is a subtler future, and for that reason alone, it may be the one the wafer was built to serve. By the end of this investigation, the wafer looks smaller than the question it carries, and more important. It does not prove which theory was right. No artifact like this could. What it proves is that the anomaly outlived fashion, that generations of astronomers kept returning to the same disciplined pattern. Visible matter was telling them too much about total motion to be dismissed as coincidence. That is the final recontextualization. At the beginning, the etched acceleration ring seemed almost like a talisman. Now it reads as something stricter, a checksum against self-deception. A future analyst could compare any new simulation or alternative gravity prescription against the same family of galaxy curves and ask a brutal question. Are you predicting the pattern or merely absorbing it? That remains one of the deepest distinctions in science. A theory earns trust when it survives data it did not arrange. And so, the wafer's final implication reaches beyond galaxies. It points to a general lesson about modern physics. The hardest problems are not always the ones with the biggest discrepancies. Sometimes they are the ones where nature appears to be offering an elegant relation, but refuses to say whether that elegance belongs to fundamental law or to collective behavior emerging from many messy parts. Galaxies may have done exactly that. They may have presented astronomers with a pattern as clean as a law, inside a universe that is anything but clean. The strongest competing viewpoint still standing is clear. Advocates of modified gravity can reasonably say that no amount of cosmological success elsewhere erases the peculiar economy of galaxy rotation curves. If visible matter repeatedly predicts acceleration with near minimal freedom, perhaps that is not an accident of formation, but a clue that gravity changes character at low acceleration. On the other side, advocates of dark matter can just as reasonably answer that clusters, lensing, and cosmology already show unseen mass is real, so the burden falls on galaxy formation and dark sector physics to explain the regularity without discarding the wider framework. That is where the archive leaves the case open, not in confusion, but in narrow disagreement. Would galaxies actually force a new law of gravity if future measurements drove the scatter around the acceleration relation even lower than standard feedback models can naturally reproduce? Or would that only tell us that the dark sector has structure we have not yet learned to model? That is the assumption this future depends on. Whether the cleanest pattern in galaxy dynamics belongs to gravity itself, or to invisible matter, learning to organize around ordinary matter with astonishing discipline. Let me know in the comments.